standard data, then you measure the deviation.
Yeah, we have by entering the configuration, we'll be able to create a baseline. And then when we are measuring the signal, both gets compared.
So means you are taking, when you put your system, that is the best operating condition, the machine, then you compare it.
Not required, sir. We can install at any point in time. We can install it.
So suppose if there is a condition, example, there is a deviation already, there is an issue with the engine, and then you install, so that the system takes that as a standard data?
No, no, sir. System does not take anything from the engine as a baseline. The baseline is created by the system based on the configuration of the engine, which is the number of cylinders, number of flywheel teeth, etc.
Okay, means depending on the number of RPM and the number of the cylinders, you have a standard data.
Already, yes, sir.
Thank you.
Actually, it's a little revolutionary concept on measuring the revolutions per minute. So it's a little difficult to understand, sir. It took me 7 years to understand. Only I got convinced only after seeing Narendra's presentation today. So
no, I am very clear. No, obviously, is a variation of the speed which they are measuring as a data. So only I had a confusion whether that bearing clearance deviation you take.
No, it's only not on space. It's only in time domain. So anyway, I think it's probably you can discuss with him a little later. It's a little difficult to fathom that we don't even need to use a peak pressure meter to understand the PV diagram at all. And it's a little revolutionary concept, definitely. But we have tried it on few of our ships. It seems to be working. In fact, the torsion meter is currently been installed on the recently commissioned indigenous aircraft carrier, INS Vikrant. It's running on trials. So Narendra, you have earned your place here.
Okay, thank you, sir.
So with that, let me move on to the next young speaker, which is Anant Ajit Kumar. You're here? Yeah. He's presently working as the assistant surveyor in the Indian Register of Shipping. They are actually our platinum sponsors, so we have to be more respectful to the speaker. So, Anant has completed his BTech in Naval Architecture, as well as MTech in Marine Engineering. It's a great combination from Cochin University of Science and Technology, QSAT. He has worked as a trainee engineer at Vijay Marine Shipyard in Goa, after which he joined Indian Register of Shipping last year. And he is working on projects related to seakeeping analysis and ship stability in waves. So today he's going to present a paper on prediction of wave bending moment for a ship at site and en route. This paper has been co-authored by two more gentlemen, Mr. Amrish Negi, who's also from IRS, joined earlier in 2006, and Dr. Suhas Vanmane. He is also working with Indian Register of Shipping since 2002.
Yeah. Thank you, sir. Thank you for that wonderful introduction. Respected dignitaries, authors, and various experts from the shipping industry. So my paper is on prediction of wave bending moment for a particular site and route. But I should mention it's deviating slightly from the section theme, that is ship machinery and maintenance. But don't worry, I've kept it away from the technical side, and I kept it as short as possible. It's more related to seakeeping analysis and the wave bending moment prediction. So basically, it's a methodology to predict the maximum wave bending moment that a ship can undergo at a particular environmental location, based on which is derived based on the wave data of an environmental location. It's mainly for the emergency response service to predict the shortest and safest route to a repair dock after a vessel has undergone damage. So without further ado, I will proceed to the introduction. I think it's... Yes, it's coming. Okay. Yeah, yes. Yeah, thank you. So, as you all know, after a vessel damage has taken place, like after a vessel accident, like grounding, collision, etc., there are various corrective actions that should be taken by the crew members or the ship management to restabilize the ship or bring the vessel back to safety. But these corrective actions are not always obvious because it's based on various analysis, like prediction, like the reserved prediction of the reserved buoyancy and estimation of the residual strength of the vessel. So these analyses require a certain time, which might not be preferable during an emergency. So what we did was so what happened? Like various classification society decided to overcome this problem by introducing something called the emergency response service, which is an integrated assessment of the ship's strength and stability of the damaged ship within a short period of time. So basically, it's like a yearly subscription. Like the vessel can, ship owner can subscribe to the emergency response service, and it's a 24-hour service. So after a vessel accident has taken place, they have already pre-modeled data of this ship, which is stored in a database. Actually, emergency response service is a shore-based service working at 24/7. And they have pre-model data of all the ships which have registered to the ERS. And based on the damage, they'll immediately predict, based on this model, they'll immediately predict the residual strength and the damage reserved buoyancy of the vessel, and they will report it back to the crew members so they can take the required corrective actions. And basically, my paper is focusing on the strength assessment of the vessel. That is, it's a methodology to predict the maximum wave bending moment that a vessel can undergo, that the vessel might undergo at a particular environmental location. And in order to do this, it's an ideal method is through seakeeping analysis. That is, I'm not going much into the technical side. That is, based on the mass distribution data of the ship and the vessel model, they'll do something called they have something called the strip theory program, and based on that, they'll predict something called RAO, which is the response of the vessel at an amplitude, unit amplitude of wave. And after that, they have to do the spectral analysis to predict the extreme wave bending moment that the vessel might undergo at a particular environmental location. But these seakeeping analyses take some amount of time, and these are not preferable during an emergency. I think it takes. Yeah. So basically, our methodology focuses on prediction of wave bending moment through something called environmental severity factors, which is nothing but a reflection of the environmental data of a particular area that the ship is located. And it is mainly derived based on seakeeping analysis. I should mention that we are not avoiding the seakeeping analysis, but we are deriving when the vessel registers for ERS. At the starting itself, we'll derive something called environmental severity factors through seakeeping analysis, and we store it in a database so that we can use it to predict the maximum wave bending moment through these environmental severity factors. And basically, I'll be explaining what is environmental severity factor, what exactly it is, and I'll be suggesting a method to create a database for these various ESF factors and how to estimate the maximum wave bending moment that the vessel might undergo at a particular environmental location. And we can use this methodology to predict or identify the safest route to a repair dock after a vessel has undergone a hull damage. Yeah, so as you can see from this blue map, worldwide map, these oceans are divided into various boxes. And these boxes are nothing but, it represents the environmental conditions. You can see a table of a particular box. This is nothing but the representation of all the sea state that that oceanographers has calculated, and they're averaged out with the help of something called scatter diagram. These values are nothing but the probability of all the sea states that can happen in that particular locations. And each of these boxes have their own scatter table. And there are organizations like the British Maritime Technology that provide these data, scatter tables to be precise. And we can use these scatter tables to predict the ship responses for various particular environment. And basically I told you that in order to predict the extreme wave bending moment, we need to, the ideal method is to do a sea-keeping analysis, and which requires a amount of time. But we have found a way to do this without, we are not avoiding the sea-keeping analysis, but we have found a method to derive factors using this sea-keeping analysis that can represent the value of a particular environmental location. Basically, what we are doing is we are estimating the maximum wave bending moment that the ship might undergo in the North Atlantic environment. And as you all might know, that North Atlantic environment is the consisting of the worst climatic conditions, and all the class rules, formulas, empirical formulas are developed based on the North Atlantic wave conditions. And all the compared to the other environmental location, the severity is much lesser. So what we have done is we have derived a factor called environmental severity factor, that is a ratio of the particular location, the extreme value predicted on the particular location of a vessel to the maximum wave bending moment, extreme value predicted for North Atlantic wave environment. So this is nothing but the ratio of the extreme value of a particular location of the vessel and to the North Atlantic, extreme value of North Atlantic wave environment. So what we just do is we just multiply this environmental severity factor with the class rule to predict the wave bending moment. And with that, we can estimate the maximum wave bending moment that the vessel might have to undergo at a particular location that the vessel is on. Takes a bit time. So now I'll be telling you how to create, how to use these environmental severity factors practically. First of all, what we are doing is we are creating a database consisting of, for each vessel, it will vary, the ESF factors will vary, and it's a function of vessel's loading condition, speed, and the location of the vessel. So what we are doing is after a vessel has registered to the emergency response service, we'll find out what is the ship. As you know, the ship has various loading conditions, and the container ships and tankers have around 50 loading conditions. So it's not easy to enter all of these data into the database. So we just developed a shortcut method, like we can estimate the ESF for the loading condition with the maximum displacement and the loading condition with the least displacement. That is, we can consider two loading conditions, the fully loaded condition, and the ballast arrival condition. And based on this, we'll identify the ESF factors for different fluid numbers. And you can see there's a blue line and the red line. These are nothing but the ESF factors estimated for two different loading conditions at a particular environment. Preferably, it will be the fully loaded condition and the ballast loaded condition, and will derive second-degree polynomial equations based on this. And we can take the factors like put the constant from the second-degree equations and feed it into the database for each of the environmental location for fully loaded condition and the ballast arrival condition. And based on that, we can estimate ESF factors for any loading condition through interpolation. What we'll be doing is, first of all, we'll be selecting the loading condition and displacement, and based on that, we'll identify the ESF factors for different speeds of the vessel. As the speed of the vessel increases, the ESF factors also increases. So we can identify the ESF for a particular speed, loading condition, and the location. Suppose if you want to find a ESF for a particular location, we can just interpolate between these maximum loaded condition and the minimum loaded condition, and we can estimate the ESF factors for that particular loading condition for whichever speed that we want. And this is just whatever I have explained, how to derive the ESF factors based on the loading condition, displacement, and the location. And as I told you, like we need to feed that. We need to have these ESF factors for each of the environmental location that I showed you in the map. And this methodology can be used to, in the starting I told you, this methodology can be used to estimate the safest route to a repair dock using this ESF factors. So I'll show you how to do that exactly. Suppose a vessel is damaged. Suppose these are different zones, zone numbers that I showed you before.